Recall that we started our series with Kroneker's dream. Previously, Kroneker and Weber have managed to prove that every finite abelian extension of Q is gonna lie inside some cyclotomic extension of Q. Weber then wondered if there is some kind of analog for imaginary quadratic extension of Q. Since cyclotomic fields are just Q adjoining special values of the exponential function, he surmised that if K is an imaginary quadratic number field over Q, then every finite abelian extension of K is gonna be contained in an extension of K obtained by adjoining special values of some automorphic functions. This is called Kroneker's Jugendtraum, i.e. his dream of youth. Solving Kroneker's Jugendtraum is part of Hilbert's 12th problem. Hilbert conjectured that every finite abelian extension of an imaginary quadratic number field K can be generated by a special value of the elliptic modular function J. However, put as such, that statement is not accurate because one would also need roots of unity. So let's assume that's what Hilbert meant. His claim is that every finite abelian extension of a number field K is going to be generated by some roots of unity together with some special values of the elliptic modular function J. Now, Hilbert was able to prove this for every odd degree abelian extension of K. Let K be some imaginary quadratic number field, then Hilbert showed that every odd degree abelian extension of K is gonna lie inside some extension of K obtained by adjoining some roots of unity and some special values of the J function. Now, how about even degree extension? Well, it turns out that the conjecture does not hold in this case, and it was again Hilbert who came up with the counterexample. Not all is lost though. If instead of all finite abelian extensions of K, we only look at those that are unramified, then indeed, every such extension is gonna lie inside some extension of K obtained by adjoining some special values of the elliptic modular function J. This is the so-called Hilbert class field of K. It is the maximal unramified abelian extension containing K. Recall that we came across the notion of class fields when trying to generalize Dirichlet's theorem on primes in arithmetic progression. Recall that Weber's generalization of Z mod MZ star is the generalized ideal class group, and in Weber's terminology, Dirichlet's theorem becomes a statement about the size of the generalized ideal class group. The psi of this generalized ideal class group of K is going to be equal to the degree of the extension of L over K, where L is the so-called class field for H over K. What that means is that the K primes that split completely in L are exactly those that lie in H, with up to finitely many exceptions. Now, by Bauer's theorem, we know that such a class field would have to be unique if it exists. The next natural question is then, does it always exist? Well, Hilbert conjectured the existence of the so-called Hilbert class field. This is the class field corresponding to the ideal class group. In other words, the primes that split completely in this Hilbert class field of K are exactly the principal ideals of OK. This idea about Hilbert class field comes from Hilbert's interest in unramified extensions, as well as on the analogy between number fields and Riemann surfaces. An alternative way to think about the Hilbert class field is that it's the maximal unramified abelian extension of K. The Hilbert class field is extremely important arithmetically because its Galois group captures the arithmetic of K. In other words, the Galois group of the Hilbert class field over K is isomorphic to the ideal class group of K. Hilbert managed to prove this conjecture for the case when K has class number 2. And then Furtwängler was able to prove part number 1, 2, and 4 of this conjecture. But it was Takagi who finally proved this in full generality. Between the 1898 and 1901, Takagi was studying in Germany, partly under Hilbert. For his thesis, Takagi proved Kroneker's Jugendtraum for the case when K was Qi, using special values of the Leibniz gate function. When World War I broke out, Takagi was completely isolated from the European mathematicians. However, he was aware of Feuter's work on Chronicus Jugendraum, as well as Verwengler's work on the existence of Hilbert class fields. During the war, while working in isolation, Takagi managed to combine the work of Feuter and Verwengler to prove the following key theorem of class field theory. Takagi showed that indeed, for every ideal group of K, there exists a corresponding class field over K. Moreover, every finite abelian extension of K arises this way. That is, every finite abelian extension of K is going to be the class field of some ideal group of K for some modulus M. Moreover, Takagi showed that if L is the class field corresponding to the ideal group H, then the Galois group of L over K is just going to be isomorphic to the generalized ideal class group corresponding to H. However, Takagi didn't give an explicit isomorphism, and this map was later established by Artin. But this isomorphism alone, without needing the explicit map, gives us the first part of Hilbert's conjecture. To find an extension of K whose Galois group is just going to be isomorphic to the ideal class group of K, we can use Takagi's correspondence by taking the modulus M to be 1 and the ideal group H to be Pm. In that case, the corresponding generalized ideal class group is just gonna be exactly the ideal class group of K. Therefore, by Takagi's theorem, the corresponding class field is gonna have its Galois group be isomorphic to the ideal class group of K. Thus, this proved the first part of Hilbert's conjecture on the existence of Hilbert class field. Now, with regards to the third part of Hilbert's conjecture, which is about prime decomposition in the Hilbert class field, Takagi actually proved a more general statement about prime decomposition in any class field of K. This theorem says that if H is an ideal group with modulus M and class field L, then for every prime of K not dividing the modulus of H, we'll have that P is going to be unramified in L, and that the inertia degree of P in L over K is just going to be equal to the order of P in the generalized ideal class group corresponding to H. But remember, we just mentioned that if we take M to be 1 and H to be Pm, then the generalized ideal class group corresponding to H is just gonna be the ideal class group of K. And moreover, the class field corresponding to H is just the Hilbert class field of K. So then in that case, Takagi's theorem becomes part 3 of Hilbert's conjecture. This says that the inertia degree of any K prime P inside the Hilbert class field should be equal to the order of P in the ideal class group of K. So that was how Takagi's theorem implies part 1 and 3 of Hilbert's conjecture. Up next, we're gonna discuss how Takagi's work implies part 2 of this conjecture, and more generally, we wanna discuss how his theorem gives a generalization of Kronecker-Weber.